is clear and you're able to see my. Okay, thank you. So in the previous class, okay, we have discussed the silicon controlled rectifier. Okay. Right, silicon controlled rectifier, in short SCR. Okay. Now the construction of this device is very simple. Okay, very simple construction. We have four regions. Okay, we have four regions, P N P N. Okay, so total four regions. First region, okay, and then the second region, okay, and then third region, okay, okay, the fourth, right? Let me join this. Okay, right. So what are the four regions means? Okay, what are the four regions, right? So we are discussing silicon controlled rectifier, okay, which simply has four regions. What are the four regions? P region, N region, P region, N region. Okay, P type material, N type material, P type material, N type, right? And the outermost P type material, this region, this is the anode. Okay, right? This is the anode. The outermost N region, this one, this is the cathode. Okay, represented by K, right? And then the P region, this one, this is the gate terminal. Okay, so we have three terminals: anode, cathode, and then the gate. Okay, the outermost regions are heavily doped. What are the outermost regions? This P region, it's heavily doped. Okay, so I will write more number of holes here. Okay, heavily doped, so it has more number of holes. Okay, I will represent more number of holes. Holes are positive charge, isn't it? So that is the reason I am mentioning more number of positive charges. Likewise, the outermost N region is also heavily doped. Okay, right? Outermost regions heavily doped, both P and N. So outermost N region is also heavily doped. Heavily doped means more number of free electrons. Okay, so I will represent more number of free electrons. We know that electrons are negatively charged, so I am putting minus sign, right? So outermost regions are heavily doped, whereas the inner regions are lightly doped. Okay, lightly doped means, okay, N region, you know, okay, whenever we have doping, we have free electrons. Lightly doped means fewer number of, okay, fewer number of free electrons. Okay, I will write only fewer number of free electrons. Electrons are negatively, okay, charged, so minus sign. Likewise, this region is also, okay, lightly doped, so fewer number of holes. Holes are positive charged, right? So coming to the construction of SCR, what we need to remember here is the outer regions means this one as well as this one. Okay, the outer regions are heavily doped. Okay, they are heavily doped. Okay, right? Whereas the inner regions are lightly doped. Okay, the inner regions, these two, okay, this one as well as this one. Okay, these inner regions are lightly, okay, lightly doped. So this is the construction of the SCR. P region, N region, P region, N region. The outermost P region is anode. The outermost N region is cathode. Middle P region, remember, okay. So this middle P region is the gate, okay, right. So obviously any device, what you have is you have metal contact. So there is a metal contact here, okay. There is a metal contact here, and then there is a metal contact here, okay, right. Just contacts to the device. Okay, anyway, next here, what happens in SCR is, okay, suppose you forward bias, okay. What do we mean by forward bias? Forward bias of the entire device means positive here, okay, and negative here. If you connect positive at anode, negative at cathode, it is forward biased, okay. So when the device is forward biased, right, okay, when the device is forward biased, then, okay, the current through the device not only depends on the anode cathode voltage, but it also depends on the gate current, okay, right. In simple words, the gate current determines when the device is on, okay, right. Hence this device is known as current operated device, okay. This device is known as current operated device. Okay. Why it is known as current operated device, right? The current, the anode current, okay, right, is not only dependent on the anode cathode voltage, but also on the gate current, okay, right? Hence it is current operated or current controlled device, okay, right? You know, BJT is also current controlled device because the input current controls output current. Same here. Your gate current controls anode current, hence this is current operated device. Okay. Now the symbol of this device, okay, is very simple. So what do you have here? PNPN. Okay, right? So the symbol is somewhat similar to that of a PN junction diode. Okay, the symbol is somewhat similar to that of a PN junction diode. Okay, PN junction diode, what it has? It has anode. Okay, it has cathode, right? So symbol is very much similar. Additionally, what you have is you have the gate terminal. Okay, additionally we have the gate terminal. Okay, or you call it as gate trigger. You call it as the gate trigger. So this is the symbol of the, okay, SCR, right? Now what we will do is we will consider two cases. Okay, first, when gate is, okay, you have the gate terminal, isn't it? When the gate is open, how the device behaves. Okay, next case, when the gate is closed, how the device behaves. Okay, these two cases we will consider next. Okay, next we will consider those two cases, right? So any doubts so far, students? So simple structure. Okay, structure is very simple. Outer two regions heavily doped, middle lightly doped. Okay, and because the gate current controls the output current, okay, it is current operated device, right? Okay. Next, so what do you mean by current operated device? When the device turns on, you can actually control by the gate current. Okay, right? So that is why it is current operated device. Next, any doubts so far, students? Okay, so here we will consider two cases. Okay, we will consider two cases. Let me choose different color. So I'll go for case one. Okay, so case one, when the gate is open. Okay, so what do we mean by gate open, right? What do we mean by the gate open? Means here, okay, we don't connect anything to the gate, right? Whereas we connect supply at anode and cathode. That is what we mean by gate is open. Okay, so now what I will do is I will draw like this. Okay, the same device. Instead of drawing horizontally, I want to draw it vertically. Okay, just okay. I will move this little up. Okay, and then okay, right. Then the four regions we have. Okay, we have the okay four regions, right? Okay. Okay, right. So this is the okay structure of the SCR. Okay, structure of SCR. P region, N region, P region, N region. Okay, right. Only now we are representing it vertical. Okay. So this one is P. Okay, N, and then okay in the textbook just they have written inside. So I will write it inside anywhere you write, no problem. So P N P N. Okay, right. Now gate open. So this is the gate terminal. This is the gate terminal open. Open means we are not connecting anything to the gate. And now let us consider the case of forward bias. Okay, we will consider the case of forward bias. What do you mean by forward bias? P side positive, okay, right? P side positive, N side negative is forward bias, okay. So here we will connect, okay. So P side will connect positive, okay. P side will connect positive, okay. So this is forward bias, right? N side we are connecting negative, okay. So what happens under forward biased conditions? See here we have three junctions. We have three junctions. This is junction J1, okay, J2, and then junction J3. Okay, we have three junctions J1, J2, J3, right? So these junctions, now let us see whether they are forward biased or reverse biased. What happens to J1? See, if you see J1, at J1, okay, positive voltage is connected on P side. So J1 is what biased? J1 will be forward biased. Okay, quickly answer when question is asked. Quickly answer so that the class will be exciting. Okay, so J1 is forward biased. Next, what about J3? Negative is connected on N side. So J3 will be what biased? Same polarity means forward biased. Okay, so this is also forward biased. Okay, now what happens? Forward biased means, okay, first J1 is forward biased. J1 forward biased means the positive goes to P side. Forward bias means conducts. Okay, so this positive signal, this particular positive signal will pass through J1. It will reach the N region here. Okay, likewise, the negative signal will come here. J3 is forward biased, so it will cross this J3, and now the negative signal will come to the P region. Okay, so with respect to J2, what is happening with respect to J2? See, at J2, okay, at J2, the positive signal is coming to N side, okay, and at J2, the negative signal is coming on P side. So J2 will be reverse biased. Okay, so junction J2 will be reverse biased. Okay, so what I will do, I will represent a reversed bias. Okay, I will shade this region. This is the, okay, this is the reverse biased, okay, junction. Okay, right? So under forward biased condition, when the entire device is forward biased, J1 is forward biased, J3 is forward biased, whereas J2 is reverse biased. Okay, right? Now, because of this, how the device characteristics they change. Okay, now we will consider the case. What happens when we gradually increase this forward voltage? Okay, so first of all, we can name this voltage as forward voltage. Okay, we can name this voltage as forward, okay, voltage, right? This is the forward voltage. Now we will consider what happens if we gradually increase this forward voltage. Okay, so x-axis I will draw. Okay, x-axis I will draw. Okay, just a minute. Okay, I hope that is a straight line. Okay, right. Now, this is the forward voltage. Okay, this is the forward voltage. I will represent it as, okay, in the book we have represented it as Vf. So we will, okay, we will represent it as Vf. Forward Vf, okay, forward voltage. right? Now, what happens when we gradually increase this forward voltage? Okay. Now, see, this junction is reverse biased. Okay, right? This junction is reverse biased. Okay, right? So, suppose we have pipe. Okay, suppose three valves in series. Okay, you have a pipe, three valves in series. If one of the valve is closed, okay, the entire water flow is stopped, right? So what happens here is, because this junction is reverse biased, that will block the entire current. Okay. So what happens when we gradually increase the forward voltage, because the junction J2 is what biased? Okay. Junction J2 is reverse biased. Current is negligible. Okay. But as you gradually keep on increasing the forward voltage, you know that the junction will break down. Okay. Any PH junction, if you increase the reverse voltage, the junction breaks down. Okay. So when the junction breaks down, then what happens? The current will, after that point, the current will increase. Okay. So if you gradually keep on increasing the forward voltage, at one point the junction breaks down. Okay. That voltage is called as breakover voltage. Okay. That voltage is called as breakover voltage, represented by VB naught. Okay. This is forward. What is VB naught? Forward breakover voltage. Okay. What is VB naught? It is forward breakover voltage. Okay. Now what happens after this point? After this point, the current, okay, through the device will increase. It will start to increase. Okay. So what happens? From this point, it will immediately jump here. Okay. The characteristics of the device. Okay. This is a straight line, right? The characteristics of the device will be such that it will jump from this point to, okay, this point, and then thereafter it simply follows like this. Okay, straight line, right? So these are the characteristics of the SCR under forward biased condition, especially when the gate is open. Okay, especially when the gate is open, right? So this is VF, and obviously this is the forward current IF. Okay. So we have discussed forward biased condition. What do you mean by reverse biased condition? You know, very simple. Just to exchange the polarity of this battery, that gives reverse bias condition. Okay, right? Because drawing is taking a lot of time. What I want to do is I want to simply edit this. Okay, right? I want to edit this because simple. Reverse bias, next case, reverse bias. Okay, reverse bias means same structure. Okay, at P side we will connect negative, N side we will connect positive. Shall I edit this? Okay, because drawing is taking a lot of time. Shall I edit this? Is it okay? Students, quickly answer. Shall I edit this? Or anybody still copying? Want some time? Do you want me to draw again? Yes, fast, please. Okay, no response, no problem. I will draw again. Okay, so next what we will do is we will consider the case same. When gate is open, text reverse bias, what happens? Okay, so when gate is open, we are considering the case of reverse bias. Okay. Okay. I will do one thing. I will draw a bit lower. Okay, so that right. I'll draw here. Okay. So when gate is open, we already discussed forward bias. Now we will consider reverse bias. Okay. Reverse bias, very simple. You draw the PN, PN. Okay. P. Okay. So four regions. 1, 2, 3, 4. Okay. Four regions. Okay, that is straight line. Somehow there is some problem. Okay, right. So the four regions, right? What are the same structure? Same structure, repeat. PN, PN. Okay. Then junctions J1, J2, J3. Obviously, okay. Obviously, we have discussed that the top P region is the anode, the bottom anode A. Okay. The bottom end region is cathode K. Okay, right? All this we have seen. So here same we will consider. Okay, this is the okay P region. This is the N region, and again P region, again the N region. Okay, the topmost P region. This one is the anode. Okay, the bottommost N region. It is cathode. Middle P region. Okay, is the gate, and we are considering, remember, we are considering the case when gate is open. Gate open means we didn't connect anything to the gate. Okay, we are considering the case when gate is open. We are not connecting anything to the gate. Okay, so here we are now considering the case of reverse bias. Okay, reverse bias means, right, we have already discussed that P side we have to consider, okay, P side we have to consider the negative, N side we have to consider the positive. Okay, that is the reverse bias condition. So this one we will join here. Okay, this one will join here. P side negative. Okay, because reverse bias. P side negative, N side positive. Now earlier we call this voltage as, okay, we call this voltage as forward voltage. We can call this voltage as reverse voltage. Okay, we can call this voltage as reverse voltage. Right? So this is reverse bias condition when gate is open. Case 1, gate is open. Okay. Now what happens here? Again, we have the three junctions J1, J2, okay, and then J3. Right? Negative at P side. So J1 is reverse biased. Okay. What about J3? J3, see here. J3 positive at N side. So J3 is also reverse biased. Okay. Right. J3 is also reverse biased. What about J2? See this junction. Okay. With respect to this junction, positive is connected at P side. Okay. And from top, negative is connected at N side. So this junction will be, okay, this junction will be forward biased. Okay. See, very simple. When the overall device is reverse biased, top and bottom junction reverse biased, middle junction is forward biased. Okay. Whereas this case, it is reverse. When overall device is whatever the overall device is forward biased. So top and bottom junction is forward biased, middle is reverse biased. Okay. Next, overall device reverse biased means top and bottom junction reverse bias, middle is opposite, so forward bias. Okay, simple, right? Now what happens here? Reverse bias, okay, whenever device is reverse bias, what do we have? Okay, we have depletion region. So this whatever I have shaded, okay, let me take the same color. Whatever I have shaded here, that is the depletion region. Okay, we know very well that under reverse bias condition, we have depletion region. Okay. Same here. Wherever we have reverse bias, we have to consider the depletion region. So where all we have reverse bias here, this junction. So there will be a depletion region across J1. Okay. Next, there will be a depletion region across J3. Okay. Right. So what happens when we gradually increase this reverse voltage? Okay, we know very well that reverse voltage we will consider in this quadrant. Okay, right? So when we gradually increase that reverse voltage, what happens? Because we have reverse bias junctions. Okay, you know very well whether one or two. Okay, as long as you have a reverse bias junction, the current is negligible. Okay. So only small leakage current will flow. Okay. Only a small leakage current will flow. Let me choose another color. Okay. Only a small leakage current will flow. But you know very well that after some point, any junction will break down. Okay. So even this, okay, even this particular device will also break down. Okay. So the characteristics will be like this. And this particular, okay, this particular point is called as the breakdown voltage. Okay. Okay, represented by VBR, it is the breakdown voltage. Okay. Now, if you see these characteristics of the device from this point, okay, from this point to this point, right? Okay, the device is off. This is called as reverse blocking region. Reverse blocking region. Again, in the forward also, again in the forward, from this point to this point, the device is off. This is called as forward blocking region. Okay. Here the device is breaking down. You have studied avalanche breakdown. Okay. Same mechanism is responsible here, right? Now, when the device, okay, say at this point, what is happening? The device is from here to here, the device is off. Here it is turning on. Okay. this corresponding current is called as the latching current represented by IL. Okay. So after latching current, you increase voltage, the current increases. And how to turn the device off means, suppose the forward current is here. Gradually reduce the forward current below IL, slightly below IL. Okay, slightly below IL, then the device will become off. Okay, this particular point, okay, this particular point where the device turns off, this is called as holding current. Okay, this is called as holding current, right? Okay, the corresponding voltage is called as holding voltage. The corresponding voltage is called as holding voltage. Okay, so we have seen the characteristics under open gate. Next class we will see closed gate. Okay, we'll continue in the next class.